Do you want to come over? All right. Hi, everyone. Welcome to yet another graduate seminar. And this time we have the pleasure of Dr. Alex Stokolos from Georgia Southern talking about the tangential Fatou problem. I know that this is a graduate student seminar, but sometimes we like to have the pros show up and show us how it's done.
Thank you, Vanis. Yeah, thank you for coming. And I was warned that not everybody knows. Familiar in the room, might be familiar in the room with tangential or non-tangential Fatou. So let me start with non-tangential Fatou.
Can I see the thing again?
Can I see? With the non-tangential Fatou. But first of all, it's my result joint works of my excellent collaborators, just fantastic people, Fausta Dibias, Uli Svensson, and Thomas Weiss. So Italian, Swedish, Polish, Ukrainian, international multidisciplinary team, and he is a logician. Can you imagine?
You should mention.
And so let me start with kind of classic stuff. In 1906, Paul Fatou prove a statement which looks like this one. If you have a function which is analytic or harmonic and bounded inside the unit disk, then at every point on the boundary, ER theta, if you consider an approach, non-tangential approach, what do I consider non-tangential approach? Say if we have here a circle and make an ice cream cone, and this is so-called Stolz region, and approaching the point, and I call it gamma theta, inside the Stolz region, there is a limit. So there is a limit of f of z when z approaches ei theta. Z belongs to gamma theta for almost every theta. And there are many further versions and extension of this theorem to more general settings, to Hardy spaces, to several variables.
Guys, I don't know what you know, because I don't know you. So if you have a question, the word almost.
Oh, yeah, I should say it. Yes. Yeah. Yeah. Okay. Almost everywhere means except the set of Lebesgue measure 0, which is real analysis. Yeah, kind of. You can think about this like really like a lens, and it's this is important. So a natural question, of course, after that was what would happen if you change non-tangential region to tangential region. For example, if you put your ei theta was there, make a curve gamma theta, which is tangential to the boundary, and kind of rotation invariant is a question if it's true that this limit exists for this gamma theta almost everywhere. And the answer is no, right? Which is expectable. And this is Littlewood theorem of, I guess, 1927 or something like this. And there are several proofs of this theorem. I see there are in Zygmunt's book, there is a proof using Blaschke product, but Zygmunt also get some proof using Hinchen, this Diophantine approximation theorem. So I saw 3 different proofs of this theorem. Kind of the theorem is not a great importance, but still it's interesting. There are 3 different proofs. I see. So what Littlewood proof? It's, I guess, 1927, if I'm not mistaken. That for every gamma theta, let me put this way, rotation invariant tangential, there is a bad function. There is a function which is harmonic and bounded on in the unit disk, such that the limit of f of z approaches ei theta and z belongs to this gamma theta does not exist almost everywhere. And there is a work by Aikawa who proves it might be even everywhere does not exist this limit. So, and kind of at that time it was settled, and common wisdom was that we are done with this subject. However, later on, Walter Rudin came back to this subject, and he asked 2 questions. One of
Sorry, Alex, can you change the pen because it's dying?
to change pen.
Yeah.
Let me try. I'm not sure that. Let me see this one. So Walter Rudin. The questions by Walter Rudin. So the first question: what if you consider approach region? So this is approach region, Stolz region. This is approach region. What if approach region neither tangential nor, I would put it, angular? And he conjectures that the answer is no. So Fatou theorem, for any kind of intermediate region, Fatou theorems perhaps false. And what kind of region? So let's consider some kind of tangential region at a point. Put here an angular region. And the final region will be like this one, say. The same story here. So this way, it's neither tangential nor not angular, right? And the second question was, what if, say, this gamma theta vary from, this theta. So not rotation invariant. This is rotation invariant case. And what if it's just gamma theta different in different places? Right. Here it's like this one, and say there like this one. It's another gamma theta. And can we have a set of approaching regions which is such that we have Fatou property, this Fatou theorem. So you have a limit along this region. And there were no conjectures in my understanding. So this problem was resolved, I believe, in 1984, maybe 86, I didn't remember exactly, by Nagel and Stein. And it turns out that it's not necessarily the case. So if in a section the portion of the which is within the region kind of comparable to the distance, like in a cone cases, then the answer is yes. I'm very kind of informal, but kind of I try in this talk, I try to outline idea concepts, but maybe be vague in details, or maybe even kind of inaccurate. Sorry for that. Okay.
Would it be non-tangential? That's the ratio.
Say again, what?
What ratio you mean?
I mean the area of this section to distance. Well, what we have, the length, this might be even kind of, we might consider in Rn, so kind of that. So if it's like a perturbed cone, roughly, this is what behind the proof. Of course, it's not so trivial as I say. I just try to simplify, maybe oversimplify. I'm sorry for that. Okay. But this is a nice article, and there are many follow-up articles when people develop in larger scale, in different settings, a little bit more general, etc., etc. So this question was solved. But you see, and it was like 1984, it's 40 years ago. But for a long time, this question wasn't solved. Maybe it wasn't kind of known. I learned it from Fausto, from my courses, when I used to be a visitor for a year in Chalmers in Göteborg, and Uli was and Fausto brought this problem and says there is a nice question by Rudin, nobody kind of even tried to attack. Let's try to work on that. And we start to work with that. And surprisingly, we were able to find the answer. And but let me ask you, what's your intuition tells you? I mean, let me make a vote, and safe vote, I promise you. So what do you think? Yes, no. Who's for yes? Other people, anybody who's in the room who's for yes? There exists a non-tangential kind of familiar curve such that any bounded harmonic function has a limit almost everywhere.
There exists a non-tangential?
Tangential, but which vary from place to place.
So for different thetas?
Yeah, different approach.
But still non-tangential?
Not tangential. With non-tangential, it's just Fatou, right?
But the curve is changing.
Yes.
Still
The curve is tangential but changing,
Changing.
right? That's
Right.
what you're saying.
Right. So, is there anybody for yes? No? Is there anybody for no?
I have a question though. Is it, we're talking about harmonic functions or analytic functions? Because even with this situation, for analytic functions, the answer is better than for harmonic functions.
Yeah, harmonic. We are talking about harmonic function.
And
That's
you should immediately erase this H infinity. It's a flashing
To range what?
H infinity,
Small h.
small h.
Yeah. Yeah. Okay.
We're very, very picky here.
Okay. Yeah, so is there anybody for yes? Is there anybody for no?
So, can you repeat the question?
The question, do you believe, or what's intuition tells you, that there exists a family of tangential curves which vary from point to point, such that any bounded harmonic function inside the units has the limits along those points almost everywhere?
So, at every point, there is a special curve which tangential, but nevertheless the limit exists.
Right. Almost everywhere.
There's a family of
Yeah, I will
1 for yes. Anybody else? 2 for yes.
Well, now that the big guys voted for yes, I mean, that will change some votes. I'll
Okay.
stick with my no.
How about
I would
no?
say yes.
This election is rigged.
Philip and I said no, right?
Goes for
You
no.
can't change your vote.
No,
1,
I
2.
didn't change my
No,
vote.
it's a safe vote, I promise you.
With my vote.
No.
So we have 3 at least.
Yeah.
3 at least.
So everybody, the kind of. Okay, let me put this way. So 5. Okay. Now I will give you the answer, and you will see that it was a safe.
Really?
Everybody's right.
That's why you have a logician on the team. We should
Yes.
have guessed.
That is why you were asking.
I gave you a hint.
So undecidable, and what, it depends on axiom of choice, or?
Yeah, this depends of model, ZFC model. And now we came back to Gödel, by the way, and the inspiration in particular came from.
Just a second, please. Over there you mentioned Littlewood and also mentioned Aikawa, right?
Right.
So Aikawa shows that every.
Yes.
So
There is a
for bounded
function,
analytic.
harmonic, I guess. Aikawa
Well,
boyfriend's
no,
harmonic.
I mean Littlewood reservoirs for bounded analytic, right?
Yeah, then Zygmunt gated.
Okay.
Yeah.
Okay.
Yeah, I'm sorry. So, and what I want to present to you today is the idea of the proof. And details are published in our paper in Finnish Annals. Now it's a new name for the journal. Annals of Mathematics Finnica or something. They changed the name. But, and it's publicly available, you could download. So the details are there. So what do I want to show you to outline the proof? Is how I understand the proof, because it's logic. I'm not an expert, and it's quite non-trivial, kind of. Let me put this. But what I want you to prove the following. So assuming continuum hypothesis, then yes.
Which way continuum hypothesis?
It's true. Assume that
There is no.
yeah, no intermediate. And there will be a number of reductions, but again, it's not detailed, it's just steps. But interesting steps, and I believe understandable. First reduction. I mean, not only reduction, but it's a statement which everybody can try to prove. It's a good statement for graduate students and or to assign graduate students if you are teaching Hardy spaces or this business. So to extend Fatou theorem to tangential region, which depends on function. So is the first claim that for any f of ZSA harmonic bounded, there is this gamma theta rotation invariant and tangential such that the limit f of z when z approaches ei theta, z belongs to this gamma theta, is equal, exists. There exists a limit almost everywhere. And even more, if you denote the boundary value by the same letter, and this is the limit which exists almost everywhere, L infinity function on a torus. And this happened at every Lebesgue point of f of ei theta. Okay. What is Lebesgue point? If I call this f of theta, then it is known that a limit 1 over, say, 2h, an integral of theta plus minus h over theta plus h, f of t minus f of, oh, f capital, I'm sorry, f of t minus f of theta dt is equal to 0. This is a Lebesgue point. And again, it's a real analysis.
A tangential or a non-tangential?
This is tangential, right? So we extend Fatou theorem to tangential region, but it depends on gamma this time. So for each gamma, there is this tangential rotation invariant region
For each f.
such that the limit along this region there exists and the boundary value exists, and this is the same as tangential or radial boundary value. And it happened at every Lebesgue point of the boundary value, and this is what is Lebesgue point, and by Lebesgue differentiation theorem, this has happened almost everywhere. Almost every point is a Lebesgue point for this L1 function. Okay, so which means that given a function f of z, you can always make it a little bit tangential this region, right? And there is a close to kind of almost precise description of this situation in a model case of in quite general settings given written in a paper by Dean Tien Shon in, I guess, 1999 or something like this, maybe 2000, in Russian Известия вузов journal. Известия вузов. And there is a description. But let me explain you why it's happened and give you a kind of, I hope I will give you a feeling why this, why it can be, but on an example of real variable situation. It's simpler, more transparent. So what would we mean in real, I'm sorry, it might be mine. I should return. Yeah, I should turn it off. I apologize. Yeah, sometimes, I'm very sorry. Sometimes somebody is calling me. Oh. What does it mean? What would be the real variable counterpart of that? The real variable counterpart would be for any such function f, for any f, there is a function phi of t which goes to 0, such that here I can put phi of h. Okay? This phi of h goes to 0. But this phi depends on f. And why is that? Because any function has some kind of regularity on the boundary. So in particular, this function has regularity. Say, let me explain you in a very simple case. If you measure this regularity as modulus of continuity, so omega of h f is the supremum of a norm f minus f capital. And this is L1 norm, for example. Or should I write an integral? Maybe I should write an integral. An integral, say, over torus. Then here you should put psi, deep psi. And this t an absolute value less or equals than delta. And this is h, sorry. And this is so-called modulus of continuity of a function. And it goes to 0 for any summable function if h goes to 0. And what do we know about that is that, and there is it's a kind of weak substitution for the derivative. There is no derivative, but kind of regularity. And a very popular condition in many theorems is that regularity of so-called Dini type. If you put here f of h, sorry, f over h converges. So this is, it means that this expression of logarithmic types. So there is famous Lipschitz condition, right? It's very strong. There is Gölder, which is kind of weaker, Gölder alpha, and this is even weaker. It's kind of logarithmic. So let's assume with this mild condition, which, by the way, is equivalent just to the summation f of f, f of 2 to the negative k f converges, the series converges, right? So let me explain. Say, if you assume that this happened, why this little phi exists? The problem with maximal phi.
To say that this series converges.
Yes, converges. Yes. So if you consider a maximal function, because in this business maximal function is the k player, and you consider this integral, which I will write in this form, f of theta plus t minus f of theta dt, and from here negative h to h, and supremum over h. This is an expression which depends on theta, right? And so kind of maximal function phi of f, capital F, capital F of theta. And if you put L1 norm, then first of all, this h you can change to 2 to the negative k. It's pretty much equivalent. So 2 to the negative k, negative 2 to the negative k, so 2 times 2 to the negative k, phi of 2 to the negative k. And then norm means an integral. If you move this integral and using Minkowski inequality within the integral, and this sup, now it's sup k, you change just to sum. So it will be sum k from 1 to infinity, 1 over 2 times 2 to the negative k, phi of 2 to the negative k, an integral to negative 2 to the negative k, 2 to the negative k. And if you move this integral inside, you have this f of theta dt. But clear this is less or equal than this expression that you have supremum for at t less than 2 to the negative k, which give you a modulus of continuity. So you pull it out in front, and so you may continue like less or equal the sum k from 1 to infinity omega of 2 to the negative k f divided. What's left? An integral from this to this is this expression. They gone, because this is outside, right? And what you have phi of 2 to negative k. But if this converges, you can always find phi which goes to 0, and this series still converges, right? So regardless how the series converges, always you can put here something, and the series still converges. Calc 2, perhaps, right? Calculus 2. And this is a choice for phi at this point, and then you can just interpolate. So, and this is what's behind. Behind this is a regularity. Kind of, this is very simple explanation in this case. In general, you have to do more subtle analysis with maximal function, and it's perfectly done in paper of Konstantinos Kolkov, I guess, 1977, and Mansbornik, something like that. So this is kind of very well known since in fact in kind of in this business. So this is just this is an explanation. Why is this possible? Because of regularity of the boundary value, you can always extend non-tangential region to a little bit tangential, depends on the regularity of the boundary value function. Okay. Good. So with this part, we are done. Move on.
But this statement, this is only because capital F is L infinity, because Lebesgue points are almost everywhere for integrable functions.
Right, right.
But you need L infinity for something? Or?
No, we just study kind of, it might be studied more general. We just study extension of classical Fatou theory. So second reduction is if you have f sub 1, oh, sorry, little. If you have f sub 1 of z, etc., f sub n of z, that each function has its own, say, gamma 1 theta and this gamma n theta, they are convex. So there is this here, you can say that even convex function, not only tangential. It could be even convex. And convex tangential. And but then if you have an intersection of n convex region, it's still convex, right? So you can choose gamma theta to be intersection of this gamma theta k 1 to 1, and this is convex, tangential, and Fatou for f1, etc., fn. Right? This is good region for all of them. Okay. This is trivial. Now non-trivial. Next step. Can you guess what would be the next step? So 1, n, then 1 finitely many, then
Say count something.
yes. Right. What if you have countably many? What if you have countably many? Yeah. You cannot do this trick anymore, right?
When you say convex tangential, you mean the interior part of the domain, is it? What do you mean by convex tangential?
Yeah. Yeah. So if the boundary is tangential and convex, like this.
Entire interior part is it? Because
Yeah. Mm-hmm. Yeah. Then
not only the
unit.
curve, but interior.
Yes, not only this time. See, yeah, I see that. And then now this trick doesn't work, right? Because the intersection, say, let's consider, say, this is gamma sub 1, right? So this is f sub 1, and this is gamma sub 1, right? And this is 2, and this is f2, etc., right? So this region is, this is fn, and this is gamma n, etc. And if these points approaches 0, then the intersection is radius, and it's not convex and tangential, right? So you cannot do this. And this is the tricky part. But look, this region gamma 1, it's not bad at all in general. Consider this point EI theta. Because say if you're approaching, for these families, if you're approaching 0, tangential or whatever, say for this point, sooner or later you enter the region which is good for this Fn, right? For any fixed n, regardless how narrow this tangential region is, sooner or later the curve will, the path will enter it, right? And so, and this means that even gamma 1 is a proper tangential region, right? For these n functions in this case. So in general, it's possible. And it's a good exercise for graduate students again, especially if they study this subject. So to prove that if there is tangential, countably many, if there are countably many functions of this type, that there is this one unique rotation invariant tangential region which serves them, such that Fatou theorem happened, right? So there is gamma theta, which I say convex tangential and rotation invariant, such that Fatou for this. So any function which we have in this countably many, they have a Fatou property along this region, which is one region for all of them, right? Okay, and now you can easily guess what would be the next step. So from 1 to finitely many to countably many, then what? Yes. So then you can write the collection of bounded harmonic functions in the unit disk in this way. Again, good exercise for graduate students to show there is at least at most continuum functions. So all functions which are in harmonic bounded in the unit disk can be indexed this way. Okay. So next reduction. Now time for continuum hypothesis, and not only for continuous hypothesis, but continuum hypothesis, but about one thing.
I'm sorry,
Yeah.
can you explain, because if you take any subset, measurable subset of the circle and take its characteristic function, it gives rise to the bounded harmonic function, right?
Mhm.
And the number of subset of a continuum is bigger than continuum.
Oh, to some set.
Well, I mean, the key word which you can argue with, I'm not sure, it's measurable subset. And probably that restriction,
Right. Measurable.
but it's not trivial to me. I mean, why?
Non-trivial. No, this is non-trivial. This is another reduction. We write like coefficients and kind of counter type of kind of triangular this procedure, and came up with
You mean you take Fourier coefficients?
yeah, or their coefficients, Taylor coefficients expanded, and came up that way. Okay. Now I add one more thing here. I add this things. I add
I'm sorry, but this is the same problem. Why the number of Fourier coefficients of a bounded function is bigger than number
This
of
I-
all subsets.
yeah, this is a
of a bounded
continuous.
set.
This is a continuous function inside the unit disk, right?
Well, it doesn't matter that they're continuous in the unit disk, but we take them on the circle. Any measurable function.
No, this function, yeah, we attach to any function, we made one-to-one correspondence with a boundary value at Lebesgue point. I'm maybe too oversimplified. So there is a one-to-one correspondence between the boundary value and the inner, the function which is analytic, inside the unit disk. And
Well, it's not one-to-one.
we can do it in that sense that regardless.
The same boundary values for millions of functions.
Yeah, in the sense that you change the zero values, but each boundary function inside defined unique ways Lebesgue points. And for these points, we can get these functions. Any other equivalent, because kind of the difference of measure zero, and we try to build something modular measure zero. Yeah, I won't say that this is trivial. This is what I say. Maybe what I say, I oversimplify the approach when I try to say something like this. For each, this is a f psi considered to be a boundary function, bounded analytic function, a harmonic function inside the unit disk. And there is a unique boundary value which we consider over here. Because as a variant, we have to construct this set of function, right? The set of tangential regions, right? So maybe, as I say, I skip kind of all these delicate questions with oversimplifying. Let me move on, and then maybe if time permit, we'll come back to this also. So maybe I can put here f psi of z. Let me put this way. So what's this? This is ordering, right? Linear ordering, and we can order the numbers, any sets in different way, right? So for example, if we consider n natural number, right? There is one ordering which is 1, 2, 3, 4, 5, etc., right? Or you can order it in this way: 1, 3, 5, etc., 2, 4, 6, etc., right? And then these two different orders of the same sets, right? And what's the difference here between these two orderings? Say in this ordering, linear ordering, any initial segment, if you put somewhere number, say 5, right? It has a minimal element, right? But in this order, say, or number 4, in this ordering, this initial segment from 1 to 4 has the same cardinality as the whole natural numbers, right? And therefore, these are different orders. So there are different orders, and we know there are famous Fermat's theorem, which says that you can always order sets in a way that each subset has a minimal element. We are not interested in this. We are interested in ordering when each initial segment has a cardinality less the whole set, Right? So our ordering is such that cardinality of initial segments, so say psi less than theta, is strictly less than cardinality of all natural numbers, right? Aleph 0, Aleph naught. So this is our ordering. And if we assume that,
But sorry, is your set n or 0 to pi?
sorry,
Is,
yeah, sorry, 0 to pi, of course. Thank you very much. Yeah. So what? So now we are done. Because now I can show you how to build what's the set. So now from ei theta, and assuming continuum hypothesis, this is at most countable, right? This initial segment is at most countable.
so the
Because,
natural order of 0 to pi, completely that one. Ignoring consider this other
yeah, we consider that
another order.
there is an order that this is consequence of continuum hypothesis, right? So it's at most countable. Therefore, there is this gamma theta, right? Such that it's tangential in particular, right? And Fatou. For what? For f psi when psi is ordered to theta this way, because it's at most countable set. And in this is most countable set, you can find the tangential region which serves it, right? So at this point, we put this gamma theta, which serves f psi with psi subordered to theta this way. Subordered to theta this way, right? It's at most countable, so we can do that, right? And this is a collection of tangential regions which vary from point to point, right? And now let's choose f psi of z and theta in 0 and 2 pi. So what you can see, we can consider first case. If theta is not the Lebesgue point, right, of this f psi, right? Okay, boundary value of f psi is theta, let me put this way. And theta is the Lebesgue point, right? And there we can do either this case or this case or this case. Okay? And Now let's count the measure. So psi is fixed, right? So how many such points which are not Lebesgue points? So the measure of the theta is 0. Because this is differentiation theory. This is 1 point, right? Therefore, the measure also is 0. Now this. This psi, which is ordered to this theta, and therefore it serves Fc by construction. Therefore, here we have Fatou. Right? And there, for fixed psi, this is initial segment. And because of continuum hypothesis, it's at most countable. Therefore, measure 0. So what we have? 0, 0, 0, and Fatou. And that's it. So modular, all the teeny tiny kind of real analysis and foundation of mathematics and other moments, logic, etc. The idea is in this. So I try to outline the idea and the concept, and everybody else kind of can, I mean, everybody can get it, can restore details potentially. And this published, I mean, it was reviewed. And Dima writes, there is this point when you have to be careful with labeling inner function and the correspondence between the boundary values, which it is impossible to explain in a short talk in this seminar. A good piece of real analysis and foundation is there. Okay? Thank you very much.
But this is just a part.
This is what?
This is just a yes.
This is just a yes.
Yes, right. This is there is a version with no when we invented, it's called generalized Yegorov property, which turns out to be also independent of ZFC. And if Yegorov use that model when this Yegorov, generalized Yegorov property is valid, then the answer is no.
Are you familiar with determination axiom?
What?
Determination axiom.
Yeah, there is determination axioms.
Because
Yeah.
they to do with the similar things. For example, they show that there is no not measurable, say.
Yeah. So at least it makes for me, I mean, it makes a meaning in that sense that why people didn't solve this problem for many years, in spite of the try, but because of that, because this is, and you know what happens, so that if you consider, say, these regions which you attach to point, and they vary from point to point, so if you make a radius, and on this radius you try to see the image of that curve, the intersection, what you get is non-measurable set. But after all this non-measurability, and which is again in real analysis non-measurable set, existence is related to this axiom of choice and whatever. So from kind of total non-measurability kind of within the disk, inside this approaching the boundary, on a boundary we came out with zero measure and therefore measurability. Kind of hard, I mean, tough real analysis, but again with elements of logic and as I say, I watched on YouTube Claudio's presentation for Gödel, right? And you know the story of, maybe she mentioned or not, the story of continuum hypothesis, that it was stated as a conjecture in 1990 by Gilbert, right, in his presentation. And then in 1940, Kurt Gödel actually proves that there is no way to disprove this continuum hypothesis within the ZFC. And 1963, Paul Cohen, Zygmunt's student, using this forcing technology which he developed, proves that there is no way to prove continuum conjecture. And
The original thing was stated by Cantor.
yeah. I mean, Cantor, 1887, I guess, right? And there is a legend that Zygmunt wasn't happy that Paul Cohen kind of deviated from his nice trigonometric series to this business. And when somebody kind of reported and told Zygmunt that, you know, your student Paul Cohen, he proves the second this part for counter conjecture, I mean, this continuum hypothesis, and that's a great result, and et cetera, and Zygmunt says something, I knew that the boy would come up to a bad end. Yeah.
There is another legend that actually Cantor somewhere mentioned that that's a possibility of the answer.
Could be.
What is this generalized Yegorov property? Is it too technical to say?
Yes, kind
What
of.
is Yegorov property?
That if you have a
Convergence on
convergence, then on set, then there is a subset when it's uniform. So, and then if you kind of do it uniformality in that model, then you get convergence, and therefore then no. Thank you very much.
I think we already did questions, but just to make sure. Any questions? Okay, well, I think you have another hour of soft speaking to do.
Yes,
It's a
soon.
good call about the water.
Thank you very much.